Hello everyone, my name is Andrew Jones and I'm one of the LAs for Computer Engineering 331 at Penn State, and this is the Notes, Hints, and Tips video for Lab 4. Now, I already stressed the importance of starting early in the previous lab video, so I'm not going to go into detail about that here. Just remember to give yourself enough time to complete the labs. Now, Lab 4 is a bit shorter than Lab 3, but it's no less difficult, so do start early. If you haven't already done so, you will need to complete Lab 3 before starting in Lab 4, as this lab builds off of all the modules that we've created in Lab 3. In Lab 3, we created the first two stages of our 5-stage MIPS pipeline, these two stages being the instruction fetch and instruction decode stages. In Lab 4, we're going to create the third and fourth stages, the execution and memory access stages. In the execution stage, we're going to select the value for our second input into the ALU via multiplexer, execute whatever operation we need to in the ALU, and then put the result along with EQB, the destination register, and the unused control signals into our EXE-MEM pipeline register. In our memory access stage, we're going to handle reading from and writing to our data memory. We're then going to put the data that we just read, the destination register, the ALU result that we got from the previous execution stage, and the write-back related control signals into our MEM write-back pipeline register. This here is the diagram for Lab 4. You can see on the left side here, we have all of the modules that we created in Lab 3, and then over here are all the modules that we're going to create in Lab 4. There's only 5 modules this time around, but we are going to be modifying a few of the modules from the previous lab. I'll talk more about that later in the video. Like the last video, I'm going to go into greater detail about these modules that we're implementing and their functionality, and the slides for the presentation will be made available on Canvas. Now the first module we're going to make is our ALU multiplexer. This here is going to take the inputs of EQB, EIMM32, both of these are 32 bits wide, and then our selector bit will be ALU IMM, and then our output is going to be B, which is 32 bits wide. The functionality is that of a multiplexer. If EALU IMM is 0, then B is set to the value of EQB, and if EALU IMM is 1, then B is going to be set to the value of EIMM32. Now next is our arithmetic logic unit. The inputs for this module will be EQA and B, both of which will be 32 bits wide, and EALUC, which will be 4 bits wide. The output of this module will be R, which will also be 32 bits wide. The functionality of this module is that on any signal change, the computation of EQA and B through the operation indicated by the EALUC is performed, with R being set to the result of this operation. For example, if the EALUC indicates that we should add, then the result R is going to be set to EQA plus B. If the EALUC indicates that we should subtract, then R is going to be set to EQA minus B. For the labs, the ALU only needs to be able to handle add operations, but in the final project, you will need to add additional operations such as subtract, and, OR, and XOR. If you want to implement these operations now, feel free. If you don't want to implement them now, that's fine. Just remember that you will have to do so in the final project, and I will go over these again in the final project's video. Next, we have our EXE-MEM pipeline register. This here, you've made 2 of these modules before. On the positive edge of the clock, you set the outputs to the inputs. This should be fairly self-explanatory. Next, we have our data memory. The inputs for this are going to be MR, MQB, both of these are 32 bits wide, MWMEM, and clock, these last 2 being 1 bits wide. The output of this module will be MDO, which is 32 bits wide. Internally, we will have our memory implemented as a 2-dimensional register array. This will be similar to our instruction memory, but there are some differences that I'll cover in the next slide. The functionality of this module is going to be that on any signal change, MDO is set to the value of the memory array at position MR, and at the negative edge of the clock, if MWMEM is 1, then the memory array at position MR is set to the value of MQB. I want to talk a little bit more about how we're going to implement our data memory. Creating our memory array, reading from the memory array, and assigning initial values to our memory array will be nearly identical to how we did so in our instruction memory. The only things that are really going to change are the names of the wires and registers and the initial assigned values. The initial values that we're going to assign for our data memory are provided in Part 8 of the lab document. Note that you do not need to zero fill the rest of the data memory, you only need to implement values for those given in Part 8 of the lab doc. Like our instruction memory, our data memory will be 64 words long and will read on any signal change. Unlike our instruction memory, we'll actually be able to write to our data memory. This writing will occur on the negative edge of the clock. Note that reading still happens on any signal change, so you're going to have 2 always blocks for your data memory. One will be used for reading, and which will occur on any signal change, and the other one will be used for writing, and which will occur on the negative edge of the clock. To clarify some of the signals for you, MR is going to be the address in our data memory. MR is going to be used for both writing and reading. MQB is the data to write into our data memory, if we are writing to it. MWMEM is our write enable. Note that reading occurs regardless of this value. And MDO is the data read from our data memory at the address specified of MR. Our last module for this lab will be our mem writeback pipeline register. Once again, this is a pipeline register. It's fairly self-explanatory. The outputs are set to the inputs on the positive edge of the clock. Now I want to talk about changes we're going to be making to modules that we made in Lab 3. In our instruction memory, we're going to have 2 new instructions alongside the old 2 instructions from Lab 3. This means that we'll have 4 instructions total. All of these will be load words, and these are all given inside the lab document. In our data path is going to instantiate the 5 modules I described earlier, as well as hook up all the necessary wires to them. The data path will also now have outputs from the EXEMEM and mem writeback pipeline registers alongside all the outputs from Lab 3. So you're going to keep the program counter, D-instruction out, and all the outputs from the IDEXE pipeline register. You're going to keep those outputs in your data path. You're going to add the outputs from the EXEMEM and mem writeback pipeline registers alongside these. In your test bench, all you need to do is instantiate some more wires to handle all the extra outputs that have been added to the data path. You also need to pass all these wires into your data path instantiation. Now that's everything you'll need to know for Lab 4. These tips here are the same that I presented in Lab 3, but to quickly remind you, I recommend that you put different modules into different files, that you format your code, give everything names that make sense, start early on the lab, and utilize office hours if you need help. With that, this concludes the video for Lab 4. Once again, if you need help, the times of office hours are on the syllabus, along with the emails for the TAs and LAs. Have a great day, and remember,